Okay, hi everybody. Here we are again. Hope this time is a little bit better for some people. So yeah, nice to see you. And does anyone have any questions about the course?
Yeah, I was wondering if you can go over 4.3c. I'm having trouble gaining like intuition really for the question.
What's 4.3c about?
The switching lemma and like proving the bound on your Fourier coefficients for circuit with the like log d minus 1 for a polylog and depth.
Okay. Well, tell me your thoughts on the problem.
Sure. So I guess I was thinking here that if there's like a bounded like a bound to the number of gates and the that if there's a bound to the number of gates and like there's a certain depth, then it kind of makes sense that the average sensitivity is bounded as a function of those two things, because if you have like a low depth, then you can't have such a high average sensitivity, because that would imply that like multiple bits are able to flipping multiple bits output change the output of the circuit, but you can't really have that if like, you can't differentiate between bits so well if you have a lower depth circuit.
That's possibly true. I mean, that intuition is actually quite good for showing the average sensitivity of a decision tree is not that high. But this problem doesn't ask you to prove that average sensitivity is low. It like tells you that the average sensitivity is low.
Sure. Okay.
So, yeah, perhaps that might be some intuition for why you find like this fact believable. That I'm trying to draw here, that if you know f is computable by a small circuit, then it has low average sensitivity. But that's all. I mean, all well and good to think about, but I mean that's given to you. I mean, this is what we got to prove.
Yeah, sure.
Or I mean,
So that's saying like the prevalence of like XOR functions above a certain size is small in the decision tree, which also kind of makes sense.
I don't think there are any decision trees in this problem.
Sorry, circuit.
I mean, in the Fourier expansion, yeah. I mean, I guess so. Yeah.
And I have to think about this problem some more, but I just having trouble like figuring out where to kind of get started on this.
Okay. Well, I mean, I guess figure out exactly what you have and what you want to prove is like a good first step. And then, in some sense, there's like only so many pieces to put together, and that, you know, we only know like so many facts about Fourier coefficients, and you know, there's some reason why this is like part C of a problem involving part like A and B as well. So a little bit like you kind of have to just like stir the known ingredients together on this one. But give it a think for a little minute. Maybe we can come back to this one if you have another question. I see there's like another question in the chat. We look at part A first. I was having trouble dealing with the summation on the right. Sure, let's look at part A. Keep drawing white on white. It's not the best idea. Justify the following identity from lecture. Influence on I, F is the sum over sets S that contain I. I like to write this. S contains I. That's the reverse of the element sign. You can use \n in LaTeX for that. It's like, \in spelled backwards of F hat S squared. Okay, yeah, we want to prove this. I suppose it wouldn't hurt to remember the definition of the left-hand side. This is, I forget maybe exactly how I wrote it, but like probability. If you choose X uniformly at random from all the binary strings, that F of like X is different from F of X with the ith bit flipped. I mean, I think this is how I wrote it in class. Is that right? Yeah, so I mean, the person who asked the question, do you have any thoughts to start on this?
Yeah, I was trying to work like from both sides of it. So I guess I did start with side. So I guess the obvious first step is to just use the polynomial definition of the F.
True. You want to plug that into here?
Yeah.
Okay.
Simplifying from there.
Okay, so it's a probability that X is drawn from plus or minus 1 to the n. Yeah, I mean, I guess the point is that F of X, sort of by definition, it looks like this. It's the sum over all the monomials indexed by S of this coefficient F hat S times, well, it's like the monomial, so I'll just write like this product I and S of X. Oops, I don't know why I wrote there, Xi. Yeah, so that's F of X. And how should we write this bit?
Well, so that's where in the next step, like this will be an if and only if with just checking the subsets that I is contained in, because they're only not like the terms won't change that I is not contained in, since we only flip the ith bit.
I think I know what you're saying, but can you say
it
a bit more? Like,
okay, well, I guess I just wrote the same exact thing for this step on the right hand side, and I just said like
it's just like a little bit notationally difficult. Like, I can be like, all right, this, and now this, but like, what should I write here?
Yeah, I guess
it's probably also bad form of me. Like, just sorry to interrupt, but like, okay, yeah, we chose a special letter I here. I. So it's probably like, I mean, this is a good life pro tip too. It's probably a bad idea to write I as kind of like the dummy variable here.
Oh yeah.
Let me write that as J.
Yeah.
My J's are not too different from my I's, but okay. Yeah, but so then what should I write here in this blue spot?
Well, so I guess if we change the summation to being over I in S, then we can write the whole right-hand side as the negation of the left-hand side. Because each of those terms will be just have the ith bit flipped, so the parity will be flipped.
I see what you're saying. So you're saying like, well, I think I see what you're saying. You're saying like, okay, like what I was trying to say is like, it's kind of inconvenient here. You want to write like product over J and S. I don't know why I'm doing this in yellow. Like product over like J and S of like these things, like the jth coordinate of these things. Like if you call this whole string X twiddle, you want to say like X twiddle J here.
Yeah, and so I guess that will be the same if I is in that set and
right
flipped otherwise.
Good. So I agree. So I see what you're saying. So you like kind of cancel out all the terms on both sides that have an I, don't have an I in them. And you'll say, so this is like, you're saying this is the same as sum over S containing I, F hat S, product J and S, XJ, different from, wait, oh,
The negation.
Negation of sum over S contained I F hat S product J and S.
Yeah, exactly.
I see.
But then, yeah, I guess that's getting closer to what we want because it has the
Right.
I contained in S. But then I didn't really know what to do from there because this
Hmm.
whole thing is like a probability, right? So I didn't really know how to think about this condition.
Yes, that's a valid difficulty. I suppose like one thing that's like a little bit funny is this. Okay, what I'm about to say is going to sound weird, but like this is a real number. And see, back before we did what you said, this was also like a real number. We knew it was either +1 or -1 because like f is a function whose range is +or -1. I hope that was specified. Yeah. But now like we took this, but like it's funny because like this is like a bunch of numbers that add up to +or -1, but kind of for like a weird reason. And now we like kind of deleted some of them. We deleted the terms that had an I in them. And so we don't really know so much about what kind of numbers this can be. And then it's like a little bit weird because like if this is just like some real number and you're comparing it whether it's equal to another real number, that's kind of like a fragile thing. Like, you know, if you're like a computer programmer, it's like a bad idea to check if like two floats are equal because, you know, what is equality for floating point numbers. So I have to like worry about this like a little bit. Maybe we can even do an example. Like, I mean, my favorite example that I know off the top of my head is this like majority of 3 function x. Got like some blurriness here. Let's see if I can undo that. Well, anyway, this happens. I happen to know this one is like a half x1 plus a half x2 plus a half x3 minus a half x1 x2 x3. And kind of like I was trying to say, like it's a little bit funny. Like this is, you know, it's got like some halves in it. So like it's like a mild miracle that like when you plug in like +or -1 values here for the x's, that this always ends up as +or -1. And indeed, let's say we're concerned about the influence of the first coordinate on the majority of 3 function. That's like the probability in a little mini election with 3 people governed by majority, that the first person's vote like makes a difference. You know, this expression here where we only take the terms that include I guess that just would be, here I is 1. So there'd be like a half x1 minus a half x1, x2, x3. And I guess this side is, well, it's the minus of that. So what function is this? Like, does it have a semantic meaning?
I'm not sure yet. I'm thinking.
Well, we can make a truth table. x1, x2, x3, this green thing, mystery quantity. Let's see. Plus, 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 minus, 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 plus, plus, minus, minus, plus, plus, minus, minus, plus, minus, plus, minus, plus, minus, plus, minus. Now I have to plug it in. Let's see. Doing like x1, x2, x3 here. That's you can maybe make a column for that. Let's do that. x1, x2, x3. That's like the XOR of all 3 of them. That's going to be plus, minus, minus, plus, minus, plus, plus, minus. And then we're doing like half of x1 minus that. So we're kind of taking like this column, subtract this column, and then divide by 2. So let's see, like this minus this is 0, so that's 0. This minus this is plus minus minus 1 is 2. Divided by 2 is 1. Plus take away minus is 2. Again, divide by 2 is 1. Plus take away plus is 0. Minus take away minus is 0. Minus take away plus is minus 2. So this is minus 1. Minus take away plus is minus 1. And minus take away minus is 0. Well, okay. I guess one thing is like it only, yeah, it's 0, 1, or minus 1. Let's see, when is it 0?
I mean, just looking at the truth table when the other two things are the same.
Yeah, it would seem, right? Yeah, I mean, the 0 rows, I'll just circle them. I think what you noticed here is 0. These are the same, these are the same, these are the same. And these are the same. Okay, when's it 1?
When they're different and x1 is plus.
Yeah, when they're different. Okay, well, what's left over is when they're different. And like somehow it's like, yeah, these ones, x1 is plus, these ones minus. Okay. So actually maybe we can figure it out even for this specific thing, like this green box thing is like literally this expression. This is like the negative of that. So like when is like a number equal to its negative? When does this happen?
When it's 0.
Yeah, if the number is 0. So somehow this condition is the same as like this green box being 0. Which we saw. Well, see, like now here's something. We saw, hey, presto, that occurred precisely when x2 equaled x3. So the probability of that green box being 0, I guess, is the same as the probability that like x2 equals x3, which is actually the same as like the probability that like, I mean, if you think of it as a little three-way voting scheme, right? That's when the first voter has influence, when the other two people vote the same way, because you're like the tiebreaker now. So I guess that's like illustrating the result in action. Yeah, I suppose. Well, I suppose you have to think about like whether or not it was like a miracle or like there's some kind of reason why this expression that you got. Well, it was sort of 0 exactly when on those inputs where x1's vote made a difference, or it was non-zero. So maybe that, I don't know, perhaps that holds in general.
Yeah, that's good. I'll think about that.
Yeah, I'll think about that. Think about that for a bit. Think about it. Let's see. Somebody else have a question they want to ask?
I had a question about 4.2c.
4.2c, that's this one. Let's see. What's going on in this one? Okay, you have a decision tree. Oh, it's about decision trees and about maybe their Fourier expansions and trying to learn them. Let's see, under the promise. I remember this problem. Yeah, okay. What are your thoughts?
Okay, so I was thinking that we could do something like what's described in part B, where we like generate a bunch of random examples and plug them in F, and try to, with high probability, compute each of the coefficients in our polynomial, or essentially each of our Fourier coefficients. Except that and like pick an appropriate delta so that like, we can union bound it and hope that, you know, all of them are not wrong. Except that I think that I ended up with a choice of delta that makes it poly n rather than n to the O log n, which seems not good.
Wait, sorry. Yeah, there's a twist in that little story where you like started describing, you know, your thoughts for the algorithm. And I was like, okay, but then like it ended with a technical question about delta. So,
Oh, yeah. So I
which is all
think
fine, but like, so wait, you said, I mean, should we address the delta business? You said that what was?
like we needed to pick a delta
Mhm.
for when we were doing our choosing like random examples and plugging them into F in order to like make sure that in the end with high probability all of our coefficients are good.
Uh-huh.
And I think that's might be the part that I'm messing up on because when I try to do that I come up with a delta that gets the wrong like time bound basically.
Well, what delta were you using?
I was using delta is O of 1 over n to the c.
Delta equals O of 1 over n to the c. Okay, that doesn't seem like too small. Is that bad?
I'm not sure. It's like this feels like then we'll draw like 4 to the h log n to the c examples, which is like about n log n-ish.
N to the c. Oh, this is like c 4 to the h log n.
Yeah, and we know h is like c log n as well.
Okay. Okay. Oh, you're saying h is c log n. So what 4 to the c log n is 2 to the log n is n. So the n to the 2c
Yeah.
times c times log n. Doesn't seem too bad. C is a constant, right? This is polynomial.
Yeah.
And
I
you're
guess
even allowing yourself more than polynomial time.
yeah. So my worry is that I've apparently made a strictly polynomial number. I apparently need a strictly polynomial number of answers, which is an open problem, and I do not think that I've
Oh, I
solved
see.
the
You think
open problem.
you think you did it too good.
Yeah.
I see. Well, now I mean I suppose I have to find out what how you're solving C. So you're saying you think you can do it with like n to the constant?
Okay, well, I guess that's what I thought.
All right, great. Yeah. Well, I am a little skeptical, but how'd you do
Also
it?
skeptical. Okay, so I think we do the thing in part B for every all of n to the c or like 4 to the h distinct s's, because from part A we know that the coefficient is not 0 for at most 4 to the h distinct s's.
Okay, so yeah, let's assume we've done A and B.
Okay. And then like we can use the union bound and say, okay, if each of them is wrong with some delta, then all of them are wrong with at most like the sum of a bunch of deltas.
Yep.
And there's n to the c-ish deltas, so that comes out to like delta n to the c. And if we want this to be like a constant, then we end up with like, well, delta equals 1 over n to the c, so that delta n to the c is like a constant.
Okay.
I'm seeing a sound giving me a correction in the chat. We don't know which 4 to the h to choose. That makes sense.
Yeah, I think I had like the same exact approach, but like we know that they're non-zero for at most 4 to the h, but we don't know which ones like to try, I guess. We only know like the ones we don't have to try are the ones where the size of s is bigger than h.
True. Yes, that is true. is part of the difficulty. Yeah.
That might be the source of my too good answer.
Okay. Yeah. Yeah. That is part of the difficulty. It's like there's not too many things you have to find, but you don't know exactly where they are. It's part of the problem. So yeah, I mean, if you imagine, I mean, it says, describe an algorithm like, yeah, think about that algorithm. Like, what is step 1 of that algorithm? What is step 2? And I don't know, perhaps if you try to write it down, you will, yeah, see maybe that you will get stuck. Yeah, perhaps you can think a little bit about that. Maybe we could take another question for now, or cycle back to something.
Yeah, I was looking through it. I think I'm almost there, but there's still something kind of weird where it's like not bounded by epsilon, but it's bounded by like epsilon times the number of things you're summing together.
So you're talking about like part C of 4.3?
Yeah. I think I just look at it a little more.
Sorry?
I think I just have to like because I just figured out like how you kind of relate like the f hat of s squared to the average sensitivity.
Okay. Well, yeah, it's you do it like this, yeah.
Oh, I guess I wasn't really using that so much as like the probability of f hat of s squared being 0 is going to be like the probability that
Wait, sorry, can I pause you for a second?
oh sure.
Probability with respect to what? Random?
Oh, sorry. With respect to like some sort of, with respect to like an s where s is greater than that, like c prime divided by epsilon times log d minus 1 n.
Sorry, I still don't get it. If you're gonna say probability, then like, you're rolling some coins or flipping some dice or choosing something at random. So like, what thing are you choosing at random?
Sure. So some s subset of like all the possible like set of n,
Okay.
where s is bigger than c prime divided by epsilon times log power d minus 1 times n. So like
You're choosing it at random?
yeah, choosing one of those at random. So basically, like the expected value, like I'm basically using that to like get the expected value of f hat of s squared.
Still, how do you mean? Like, I know it's a little hard because we don't have like a shared board so easily, but like,
Sure.
what's a math fact I can write down and stare at?
Sure. So like the probability that the probability that f hat of s squared equals 0, where s is taken from like all possible subsets of like n,
Yeah.
but s also has to be bigger than like c prime divided by
Blah, blah,
epsilon.
blah.
Yeah. Is then going to be basically the probability that like for those then if you oh wait. Right, which is like basically equivalent to the probability that there's going to be some. Well, I guess the way that I was writing that was that I actually expand out the definition of f hat of s squared, and then I swap s and a, and then I basically look at the probability that like the sensitivity of like every x within. Oh, so this is not. Oh, sorry. I just started working through this. Might have to like take a second more. But like, I was thinking along the lines of like, what's the probability? Like, what's the expected value of f hat of s squared? And then you can get that by writing out its definition, and then looking at what's the probability of like there being. I think I have to write this out a little bit more.
Okay. I mean, there's a lot
Yeah.
of symbols in this problem. But some of them are a little bit irrelevant. I mean, like this whole like blob of stuff. Oops, I'm still drawing. I mean, that's a lot of symbols, but it sort of just like recurs here without the epsilon.
Right.
Like, we can also, for example, okay, let's do our same like literal favorite example as always. F is the majority of 3. So what is the average sensitivity of this?
1.5.
Yeah, it's 1.5. That's true. So let's take epsilon to be. Let's take epsilon to be. Let's take it to be 0.8. You may imagine that like perhaps we're wondering whether the sum over s greater than or equal to 1.5 over 0.8 less than or equal to of f hat s squared is less than or equal to 0.8. Well, is it?
I mean, I'm gonna say yes because the problem says so.
That's true, but can you say yes because of some like numerical facts? What is this number? This is a number. What is it?
So I guess the size of S is like for a size of S of 2 or 3, and then
True.
that's going to be 1 minus, since the sum of f hat squared, where s the size of S equals 1. Or
True. I guess you're using the fact that like it's 0 and s is empty, but that's true. Well, I mean, I'll put you completely on the spot. Does anybody else know what this number is?
Oh, just 1.5 divided by 0.8 is 1.875. So,
Sure, that's what this number is. But I mean, like
Yeah.
this whole number.
oh, isn't it like? I mean, if the size of S is greater than or equal to 1.875, then there's only one in the majority algorithm. There's only one like set which has a positive coefficient with or non-zero coefficient,
True.
which is like V3, so it's like a quarter. Then
Yeah, that's right. It's I'm just staring at this expression down here. There's only this one, and yeah. So you get this one, it's a quarter. So this is a quarter. And well, great. Yeah, it's less than 0.8. So it worked. Yeah, that's good. How did you know, by the way, Lev, how did you know that this was 1.5?
Because like it takes 1.5, like basically the majority is determined by more than 1.5 like bits being set to 1 or -1.
Not so happy with that.
Yeah, I was kind of like just kind of guess.
Oh, all right. Well, I guess you can review the definition of the average sensitivity then.
Do you not just use the part B for that?
That's a good idea, yes.
Yeah, just like if you just use part B, then it'd be like a quarter times 3 times a quarter times 3 plus a quarter. Sorry, like it's because like there's 1, 2, and like there are 3 coefficients for like s of size 1, which have coefficient quarter
Yeah,
half, and then like 1 of size 3, which has coefficient minus half.
that's right. Yeah, I mean, you can compute it in 2 different ways. You can compute it, I mean, by the definition, it's like average sensitivity. Yellow is not easy to see. As you're saying, you can also compute it using this formula where you like square this times 1, square this times 1, square this times 1, square this times 3, and add that all up. And indeed, I think that will give you 1.5.
Oh, sure. Okay. I didn't see the formula down there.
Yeah. Yeah. Well, let's take a break from this one. We can come back to it. Is there another question?
Can I ask about 2B?
Sure, 2B. Yeah, I guess everybody solved number 1, huh? Impressive. I thought that's like tricky. Well, anyway. Yeah, sure. 2B, what's your question?
So for now, what I'm thinking the algorithm is like, so the actual f hat of x is like 1 over n and sum over all the x, and like f of x times like x s of x. That's like the actual.
Sum over, sorry, sum over x. I'm just writing something over here. What did you say here?
F of x times like
I guess this, right?
yeah, that thing.
Yes, true.
So what I was thinking is like, if we don't use all the x's here, if we only use the random examples we drawn, and like to estimate f hat of x.
Yes.
But so I think we're supposed to use like f hat of x is like an integer multiple of 2 to like 2 to the minus h or something. But
yes,
somehow I cannot.
This does help. Yes, yeah.
Yeah, and like, so if I estimate like f hat of x that way, I don't really know how to like bound the probability.
I hear you. Let me ask you this. What's your favorite value of S?
Empty set.
Great, that's mine too. I was hoping you'd say that. So let's if S is the empty set, then let me just plug it into what you wrote. Like f hat empty set is 1 over n, sum over x, f of x. Then I guess this is 1, so that's it. Okay. I'm just gonna scroll back and look at the question here. Describe and analyze a simple algorithm that given any set S. So yeah, we decided it was gonna be the empty set. That's good. I mean, we better do it at least when S is the empty set. Draw some blah, blah, blah examples and outputs a number, which is very likely to equal f hat empty set. Okay, that's cool. So let me go back to where I was over here. So yes, we have so-called random examples from F, and we're trying to pretty much figure out with high probability this quantity on the right. Yeah. So yeah. Let's play a game. You be like the learner. And you don't really have too many things you can do other than like ask for a random example, but do you want a random example?
F of 0.
Sure. Well, you don't get to pick, but like you can just say like I would like a random example.
Okay,
so,
yeah. Okay.
Oh, sure. Yeah. Well, here's my example. N, I don't know if you knew, but N happened to be 10, and there was like an H as well. Like maybe H is like, I don't know, 3 or something. Let me make a 4. Cool. Yeah, X is 0, 0, 1. Oh, 10 is a lot of digits. Well, okay, I'll do it. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. And for this X, F of X is +1. Okay. What next? Do you want another example?
Yeah.
Okay, cool. So then maybe like I'm just picking this at random. And for this one, F of X is +1. Let's say. I'll give you another example. Why not? Like, let's say you ask for another example. Maybe this one, X is -1. What do you think so far? If I was like, the machine broke, like you got to stop and guess right now. What is F hat empty set? What would you guess? Not easy, but I mean, if you had to guess, yeah. Or you can have some more examples if you want. Do you want some more examples?
I don't really see how more examples would help here.
Well, maybe. Well, we have to figure out this. I guess N is 2 to the power of 10. That's like 1024. This is all the strings of length 10. Trying to figure this out. Anybody else want to do another step of the algorithm?
Can you take the average of the values? Because
Which ones?
of the plus, yeah.
Yeah, what's the average of those? I guess it's 1/3. So if you had to stop now and you were on a game show and like you had to do your best guess for what F hat empty set is. Should we guess 1/3?
Yeah.
1/2 or 1/4.
Yeah, 1/3 is not like your smartest guess because I mean, it's on one hand, it seems like a good idea, but on the other hand, you kind of actually, there's a reason to know it's 100% definitely not 1/3. Do you know why? I mean, in some sense, for sure, it's not 1/3, right? I mean, like, look at this number. It's like the sum of a bunch of plus or minus ones divided by 1024. Like, there ain't no way that can be 1/3, actually. It could be close to 1/3, but it's, I mean, yeah, so do you have a guess? Let's see. Oh yeah, sorry, I don't have my chat like right open in front of me. Let me get it out here. In the chat. Okay, having Zoom troubles. Oh, it says used to be a multiple of 1/2 to the 4. Yeah, true. Yeah, I mean, I think that was like on a previous fact or something. It has to be a multiple of 1/2 to the 4, like a multiple of 1/, what is that, 1/16? So yeah, so like if you really had to guess, I mean, you probably want a few more examples, but if you really had to guess, what do you think would be a good guess? 5 over 16. Yeah, that's what I was gonna say. If I had to guess, if it was like the life is on the line, or maybe to put it positively, if I could win $1 million if I guessed correctly, I would probably guess 5 over 16. Cross my fingers. But yeah, maybe if I got like another, let's say I was like, oh, the machine came back online. I was like, oh, great, give me like 2 more examples. And I was like, okay, 0, 0, 0, 0, 0, 1, 1, 0, 0. That one is -1. Maybe the next one is like 0, 0, 1, 1, 0, 1, 0, 0, 1. F of x is like -1. Who answered? Gabe, what's your best? If you had to guess right now, what was this expression? What would you guess?
Let's see.
What would I guess? Yeah, hold on.
It's like close to -1/5, which is like,
yeah, if I had like
3 out of 16.
Yeah, if I had like, okay, if I didn't know anything about decision trees or whatever, I'd be like, maybe it's -1/5. But then if I did know something about decision trees, I guess I'd be like, maybe -3 over 16 would be my best guess. Yeah, I don't know if this is making sense to the original person who asked the question, but I mean, let me put it this way, like one could ask the following, one could say like, if I gave you, how many examples do you think you would need before you'd like really like be, you know, you'd bet $100 against a prize of $1 million that you'd get the right answer? If I gave you like 1 billion examples, I think you'd probably be happy, right?
Oh, can the random examples like repeat?
They can repeat, yeah. I mean, it's literally every time you like hit that button, like 1 out of the 1024 possibilities for this string is chosen at random. And then whatever it turns out to be, like you get the true value of f of that string. So yeah, like say I was being like friendly and I gave you 1 billion draws. So like, it would be like, well, this would be a very long list. Obviously, there's only 1024 different possibilities. So actually, after a while, you'd probably be like, you know what, we can stop this trade. Like, probably you'll get into a situation where you're like, literally, you're no longer giving me any new information by giving me more examples. Do you see when that will happen?
I mean, it'll definitely start happening once you've seen all the 10-digit binary strings.
Yeah, true. I mean, at that point, you'll literally know the entire truth table of F, and you'll be like, I can answer any question you want. You want me to figure out this? No problem. Like, I will know it exactly. Yeah. Now, a question of like, yeah. Actually, let's even, I don't know. Let me do one more kind of weird example. Let's say it's a decision tree of height 1. The decision tree of height 1. Is that a good example? I'll say it's a decision tree of height 0. So decision tree of height like 0. Just, I mean, like a normal decision tree is like x1, x3, x2, x5, blah, blah, blah. And then there's some leaves, like if you get down here, it's like +1 is the answer. And then if you get down to here, like -1 is the answer. +1 is the answer. -1 is the answer. +1, -1, something like this. This is a decision tree. X2. Decision tree of just height 0 is just like there are no nodes. Like the whole thing is the answer is right here. So it's either +1 or -1. Yeah. In this case, how many random examples would you want in order to bet $1 million that you know F hat empty set?
I think I just made one.
Yeah, I think it was just one example would be good enough here. This is actually like a case, I mean, you kind of know, well, you know F hat empty set is either +1 or -1. So I don't know if this was actually very helpful. This is probably not a helpful digression, but yeah. But I guess probably the most helpful digression was maybe back in this guessing game where got a few examples and we maybe thought our best guess was like 5/16, and then we got like a few more examples and we thought, okay, maybe our best guess was like -3/16. I mean, obviously you should guess like some integer over 16 in this h = 4 case. Yeah. Does this give you some idea, or maybe you still have a question? No response. All right, well, I'll leave it open then. Is there another question or a follow-up question?
Maybe I can ask 4.1 since no one else asked that.
Okay, yeah, sure. 4.1, 4.1. Oh, this thing. Yeah.
Yeah. So
yeah.
I mean, I kind of know how to do 2add relatively easily. I mean, maybe I'm wrong, but basically, if you multiply all the integers by 2 and then subtract t, then you're looking for the two integers that are one is negative of the other one in some sense.
Let's see. Wait. Okay. So you got a bunch of numbers, n numbers between 0 and n minus 1.
Yeah.
And you're also given t. You want to know, are there two numbers that add up to t?
Right.
So let's see. So like, for example, whoops, like maybe the input list is like 2, 6, 4, 8, 2, 0, 1, maybe 23, and t is 5. We want to, there's like two numbers in this list. I guess n is whatever 7 here. Oh, well, maybe it's not valid because the maximum number here exceeded. All right, so fine, I'll make this whatever, 7 and like 6 and like another 8. That should be okay. Yeah, so what was your idea for solving this?
Well, at least like if you don't have the bound, then you can just multiply all the numbers by 2 and divide by 2 and like subtract 2.5 t over 2. Sorry, multiply by 2 and subtract by t, and then if you have two numbers that are negative of each other, like then you would get you would know that would be true.
I see. So then you're subtracting t, you get like -1, 7, 3, 11, -1, -5, 9, 7, 11. Wait, so you want your point of, and you're looking for two that are like the negatives of each other?
Yeah.
They're saying that would happen, that would mean like if this one was a and this one is b, then that would be like 2a minus t is the negative of 2b minus t. Let me just figure this out. So that's like minus 2b plus t. So you get like 2a plus 2b equals 2t, t equals a plus b. Okay, cool, yeah. How do you
Yeah.
find out if two numbers are the negative of each other though?
You sort by absolute, and then you using radix sort, and then you just compare in a list.
Good, good. So, okay, so this linear time, this linear time. Now you're saying you like sort these by absolute
By
value.
absolute.
That's even linear time, but even if you're not being overly sophisticated, it's order n log n. And I think the problem allows that. Or maybe
No,
it
I
wants
think
linear time.
It's linear time, so you need
Okay.
to yeah.
All right, so fine. So linear time. So you sort them, good. And then, okay, in this case, you would get like -1, 3, 7, 7, and 9, 11, 11.
Right.
And then you like start scanning them this way. Yeah, you could like secondarily sort on their sign or whatever. And like,
Right,
I guess
right.
you could, I guess in some way you could like do a linear pass and figure out the answer.
Yeah,
I agree.
Exactly. Yeah.
Okay, okay.
So I have that.
Okay.
I think, yeah, and I mean, I assume that like there's some way to do this with FFT, but like I'm not sure exactly how. Like I've been like trying to play around with it, where I'm like, is there some way in which we can represent this as a polynomial, like this array as a polynomial in some sense, and then take the FFT of it, and then have some like and some properties of the coefficients, or sorry, I guess this is the coefficient representation, but the some property of the value representation gives us information about how the how numbers are added, or what the sum of like two numbers are, or for three numbers are, or four numbers are, something like that. But yeah, that's just like my high level intuition. I'm not sure how to like actually tell that from the n value representation of using the FFT.
Yeah, definitely. I mean, this is a problem where like if I were you, like you kind of want to metagame a little bit, like
Yeah.
you know, like it asks you to do something in like n log n time. You know,
Right.
after a lecture, we talked about like Fourier transforms and the word RAM
Right.
model. There's only so many algorithms that are n log n time, like, you know, sorting or FFT. So I can understand that. I guess you should possibly / probably also speculate that like there doesn't seem to be any like inherent relationship between like the number 5 and the answer.
Yeah.
So therefore, you should probably also work for like 6 or 4. I mean,
Exactly.
so there's that. So these are like, you know, meta clues you can get. So okay, so like we've got a list of numbers. What do you want to do? Like figure out if like some 5 of them add up to this target.
Yeah. Or k of them in general.
Yeah, sure, yeah. Yeah. So you said something about polynomials?
Yeah, I mean, I guess you can represent this as a polynomial. I mean, that
How
it's
so?
just I guess if you have a polynomial, yeah, I was somewhat unclear, but like my intuition is maybe like if you have polynomials where there's 0, like they could take on values of like 0 or 1, that the x's can take on values of 0 or 1 or something, then when like 5 of them are 1 and the sum is equal to that, then the polynomial should evaluate to t or something like that. I wasn't exactly sure though, like what a good polynomial representation would be of this.
Yeah. I mean, I do remember how to solve this problem. So my, you know, humming is kind of fake, but like, how do you like discover the solution to this problem? I mean, well, okay. What does the FFT like let you do in n log n time?
If you have coefficients of polynomials, it gives you the it gives you the evaluations of the function on the nth roots of unity.
Okay.
Or on endpoints. Yeah.
Yeah. So does that seem like the sort of thing that will help?
I guess if you're adding, so it would be like you'd have the nth roots of unity multiplied by each of the numbers in the array, and then yeah, maybe not entirely sure of that, but yeah, maybe.
Anything else is good for the FFT?
I mean, I know like the first value tells you the average, but that doesn't really help, I think.
Yeah, that's true. I guess you can work out the average in linear time. Let's see.
Naively, I would just like try all 5 combinations, but obviously that's like 2.
Yeah, that's gonna be like n to 5th
Yeah.
time.
Yeah.
Maybe I'll take some inspiration. Like I have no idea if what I'm about to say is right or not, but like maybe I'll take some inspiration from like the whole like counting sort aspect of radix sort. Like what if all the numbers were like 0 or 1? Would that help? Like I give you this long list. You know, I always imagine like, okay, what would I do if I'm there with my piece of paper? Another thing to imagine is like, what if like whatever n is, you make a small value of it. But here, like, it's a bit funny because n represents 2 things. It represents like the number of elements in the list and also represents
right. Yeah, maybe that's, sorry, I like maybe did not take advantage of the fact that you're actually given the range. I just assumed that the range was unlimited. So
I'm pretty sure, again, like from a metagaming points of view, like the fact that it's specified might mean that it's relevant. Actually, what if we shrunk that? Like if let's say every one was either 0 or 1, I mean, well, we could ask, okay, yeah, that's about the smallest possible value I could imagine. So now if I give you t is, it's hard to make it hard, 5. How would you do it? Could you do that in n log n time?
You could do that in n time. I think.
Yeah.
You could just sum everything and see if it's greater than 5.
But actually, it's already a little bit interesting. What if it like, you know, it's 0, 1, or 2?
Yeah.
So like 2, 2. Now.
Yeah, you could do radix sort, sorry, counting sort, and like count the number of zeros, count the number of ones, count the number of 2s. Maybe.
True. Actually, that's true. Although, wait a minute. Actually, now that you bring that up, it's a little bit funny. Let's say you did that, and now you're like, okay, there's like, well, there's number of zeros is 2, and like the number of ones is 10, and like the number of 2s is 1, 2, 3, 4, and like I don't know, t is let's say t is 7. Yeah. And what exactly are we trying to figure out if t is 7?
Whether some combination of the zeros, ones, and 2s can like that we have, you can add them together to get 7, but you can here just using ones.
Wait, no, what exactly is the problem asking?
Whether there's a total of k, right? Like whether there's k.
Let's say 5.
5. Okay. So whether there's 5, the sum of 5 of these digits will add up to 7.
Okay. So is there?
Yes. You can use.
How would you do it?
You can use 2, 5, right? So you can use, I guess, 3 1s, yeah, and 2 2s.
3 1s and 2 2s. Yep. What if it was this? Let me give you some more examples. What if it was this? What does this add up to? 16. What if it was like 9 0 and 7? Could you do it?
No.
True.
Just
Let me give you another one.
That,
sorry, what were you gonna say?
just because 7 is odd. And you only
Yeah,
need
true.
2s. Yeah.
What if it's this one? 14 1 1. Can you do it?
No.
Really?
Wait. 14 zeros, right? Yeah. I think you can't.
Really, really?
Am I missing something here? Because you only have 2 2s and 1 1. The total you can make is 3. The maximum you can make by adding digits is 3, right?
Does everybody agree to that?
You can reuse them, right?
Oh, I didn't see that. Oh, yes.
Yeah.
That makes sense.
So, okay, can you do it though?
Sorry, what was the?
Yeah, this was it. There was like 14 zeros, 1 1 and 1 2.
Yeah, you can still, as long as you have 1 1 and 2 1 2, you're good. You can do it.
Yeah, that's actually interesting because like now imagine you were like producing this vector, and you were like going through doing your counting sort or whatever. You're like, okay, 0. So you're like initialize things to 0 0 0. Because I don't know if some in this problem, like imagine you know in advance it's only 0s, 1s, and 2s. You're like 0. So like cool, like +1. Now I have a 0. That didn't really help that much. 1. Okay, then you're like, cool, I've got a 1. Then you're like 1. Okay, cool. Now I've got 2 1s. That's actually, there's something a little bit funny about saying that.
Yeah, it doesn't really matter.
That's true. It doesn't really matter. Like once you got that first one, you're like, okay, great, I got a 1.
Yeah.
In fact, like here you got, yeah. Once you got this 2, you're like, oh, I have 1 of everything. Like I don't even need to look at the rest of the list.
I'm done.
Yeah,
exactly. That makes sense. Yeah.
I think this observation doesn't help solve the problem very much, but I think it helps solve it a little bit.
Okay. Thank you.
Yeah, sure.
I'll meditate on it.
Yeah, I mean, one thing at least, one thing at least to know is that like, it doesn't help you to have more than 1 copy of a given number.
Right.
This may be
not necessarily distinct helps. Thank you.
Yeah. Okay, I guess we're over time, so I'll pretty much wrap it up. But if there's like any like 20-second question. No? All right, then I'll see you in class tomorrow.